Picture this. You're sitting in the exam hall. The clock is ticking loudly. You flip open your Cambridge Computer Science pass paper. Maybe you're sitting code 0417, 0478, 2210, or even the AS level 9618. You turn the page, and there it is. An intimidating 8-mark extended response question staring right back at you. Your mind just goes completely blank. Or maybe worse, you fall into the trap of doing what a student we're going to call Alex does. Alex is our classic overthinker. He looks at a complex question and just starts word-vomiting raw, unfiltered computer science facts all over the page. He completely ignores the command words and offers absolutely zero actual analysis. On the totally opposite end of the spectrum, we have Sam. Sam looks at the clock, goes into full panic mode, rushes through the entire paper, and entirely misses the specific, nuanced requirements the examiner is literally begging for. Well, welcome to the Explainer. Today, we are going to master Cambridge Computer Science concepts, and more importantly, we are going to tailor our exam answers to fit the questions perfectly, with absolutely no loose threads. Throughout this session, we are going to look at actual, flawed answers from students exactly like Alex and Sam. We're going to look at the dreaded red pen marks, and then we are going to transform them into high-level, maximum mark responses. Think of it like this. We are going to become the fashion designers of the exam hall. We're going to measure the question exactly, cut the fabric of our knowledge to fit, and tailor a completely bespoke answer. Get ready because we are about to decode the absolute secrets of the Cambridge mark scheme. Let's dive right into this. We have a highly focused, intense study session ahead of us today. We'll be alternating between reviewing the core syllabus concepts and breaking down the exact answering strategies you need to secure those top marks. We'll be covering the software divide, operating systems and HCI, mastering interrupts, translators and IDEs, and finally, looking at everything through the examiner's lens.
Section 1, the software divide. Let's start right at the foundation of literally any computer system you will encounter on this syllabus.
We need to establish the clear, unshakable division between system software and application software. Now, when the examiner asks you to distinguish between these two, this is exactly where students like our overthinker Alex lose massive marks. Alex just writes down a huge list of software names without explaining their fundamental purpose. But to get the marks, you need to prove you understand the structural hierarchy. Computer systems are built like a pyramid. You have the raw hardware at the base. Sitting right on top of that, you have system software, which exists solely to manage that hardware. And then, sitting right at the very top, you have application software, which exists for the user. Notice the visual contrast we've got here. On the left, we have applications that perform specific user tasks. Think of a spreadsheet used to organize and manipulate numerical data, or video editing software used to add color correction to a film project. Those are apps. They meet your requirements, not the hardware's. On the right, we have utility programs, which strictly fall under system software. These don't help you write an essay, they help maintain the computer itself. Take a disk defragmenter, for example. A disk defragmenter rearranges blocks of data, physically removing empty spaces left by deleted files on a magnetic drive, so that parts of a single file can become contiguous, meaning stored right next to each other. This drastically speeds up data retrieval. When the exam asks you to categorize software, remember this absolute rule. Apps serve you, the user. Utilities serve the computer. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Moving on to Section 2, Operating Systems and the Human-Computer Interface. Let's look at the most critical piece of system software you need to know and the absolute best strategy to explain it on an exam. The OS is the mastermind. It operates completely in the background, disguised from the user, but it manages absolutely everything. Looking at this wheel, we have the human-computer interface, multitasking, error handling, management of user accounts, hardware management, including all your drivers, memory management, interrupt handling, and security. Without the OS, a computer would just be an incredibly user-unfriendly box of circuits. Now, here is where we introduce the ultimate strategy. When a Cambridge exam asks you to describe the functions of an operating system, you cannot just list these bullet points. You must apply the PEL framework. P-E-E-L. Point, evidence, explanation, link. Top students structure their extended answers using PEL to ensure they actually answer the question that was asked, rather than the question they wish was asked. The point states the function. The evidence, or explanation, expands on exactly how it works under the hood. And the link ties it firmly back to why the computer actually needs it to function. No loose threads. Let's look at these core responsibilities and actually apply that PEL framework right now. Take memory management. If you just write "it manages memory," you get 1 mark, maybe. But applying Peel, the OS keeps track of all memory locations and carries out memory protection. That's your point in evidence. Why? To prevent 2 competing applications from trying to use the exact same RAM location simultaneously. That's the explanation. If it didn't do this, data would overwrite, corrupt, and the system would crash. That's the link. See how powerful that is? Or take multitasking. The OS allocates specific processor time slices to all resources and uses priority systems so that background tasks and foreground tasks are done efficiently without locking up the CPU. Think about hardware peripheral management. The OS uses specific device drivers to allow input and output to take place, managing queues and buffers to ensure the ultra-fast CPU isn't sitting around waiting for a slow printer. It performs at its absolute maximum. So when you write your exam answer, pick one of these core responsibilities and explain it deeply with Peel, rather than just name-dropping 5 of them like our friend Alex would do. Now let's zoom in on one very specific part of the OS, the Human-Computer Interface, or HCI. This has evolved massively over the decades. We started with strict WIMP environments, which stands for Windows, Icons, Menus, and Pointing Devices. This setup absolutely requires a mouse to navigate menus and select options. But now we've moved to post-WIMP touchscreen interfaces, which are everywhere on smartphones and tablets. Post-WIMP allows complex tactile actions like pinching to zoom and rotating images with 2 fingers, which would be entirely impossible to execute naturally with a standard WIMP mouse setup. This comparison is a classic Cambridge exam question. And guys, this is exactly where our rushing student Sam lost massive marks by panicking and not paying attention to the command word. Let's look at the transformation. We're about to turn red pen marks into green check marks. Let's introduce the computer science success blueprint. Notice how the high-level exam answer accurately analyzes the input methods. It states, with post-WIMP, the user doesn't need a pointing device since this only works with a touchscreen. The user simply uses their finger to carry out movements such as pinch and rotate. Look at that, it's precise, it uses technical vocabulary, it's perfectly tailored. Now, let's look at Sam's low-level answer. You can't use a mouse to do some post-WIMP functions. Also, touchscreens get quite dirty. Ouch. Sam gets literally 0 marks here. Saying a screen gets dirty is a vague, non-technical, everyday opinion. It completely ignores the core assessment objective, which is to demonstrate strict knowledge and understanding of computer science concepts. We transformed that red pen into a green checkmark by relying entirely on technical precision. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE, to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Let's look at this real examiner tip. It shows exactly why the command word explain demands a direct, focused contrast, not just a list of random facts you memorized the night before. The question specifically asked for the relative advantages and disadvantages of WIMP versus post-WIMP. The examiner's tip strictly warns, do not include disadvantages compared to other interfaces like command line interfaces, because that simply wasn't the question. Tailor your answer to fit the question perfectly, no loose threads. If you decode the command word, measure the scope of the prompt, and stick strictly to the parameters of the question, you instantly elevate your mark potential from a C to an A star. Section 3. Mastering interrupts. Let's move to our next core concept and see how this builds into the highly complex world of system interruptions. Whether it's a physical paper jam in a printer, a missing executable software file, a user suddenly pressing a key on the keyboard, or a timing signal error from the internal clock, these signals all demand the CPU's immediate attention. An interrupt is literally a signal sent from a device or software to the microprocessor, causing it to temporarily pause what it is currently doing to service the request. Buffers play a huge role in this ecosystem. Buffers are temporary memory areas. Think about printing a giant document. The data goes to a buffer first. Because the buffer holds the data, the ultra-fast CPU doesn't have to wait for the slow mechanical printer. It can go do other things. When the printer finally empties that buffer, it sends a hardware interrupt to the CPU asking for more data. It's an elegant, highly efficient system that prevents bottlenecks. By breaking the interrupt lifecycle into these precise chronological steps, you can perfectly structure your exam response to guarantee maximum points. Okay, it's time for our interactive workshop. Challenge 1, data scan. I want you to imagine a 60-second visual timer on the screen right now. Look at this complex data flow for an interrupt lifecycle. I want you to quickly extract the core trend. What happens when 2 interrupts arrive at the exact same time? How does the computer know what to do? Think about it. Scanning. The answer is found in step 3, interrupt priority determined.
You see, not all interrupts are created equal. A critical hardware failure interrupt has a much higher priority than a simple keystroke interrupt. The CPU constantly evaluates the priority, executes the specific interrupt service routine, or ISR, to handle it, and then perfectly restores the original task once the interrupt is cleared. If you write this exact step-by-step chronological sequence in your exam, the examiner literally has no choice but to give you full marks.
Moving into Section 4, Translators and IDEs, let's look at the critical utility programs that real-world programmers rely on to build functioning software. First, we must understand how to bridge the massive gap between human-readable high-level languages and the binary machine code that computers actually understand. Programmers write in high-level languages like Python or Java because they use English-like keywords. They are infinitely easier to read, write, and debug. But CTUs only speak ones and zeros, binary machine code. Translators are the bridge that solves this. This table right here is your ultimate cheat sheet for contrasting them. A compiler translates a high-level language program into machine code all in one go, producing a standalone executable file that can be distributed to customers and run without the compiler even being present. An interpreter, however, translates and executes a high-level language program one single statement at a time. It does not produce an executable file. Then we have assemblers, which translate low-level assembly language into machine code. All right, let's jump into Challenge 2 of our interactive workshop, Find the Flaw. Listen very closely to this flawed sample paragraph from a mock exam. An interpreter is great for distributing final software to customers because it produces an executable file and runs very quickly. Did you spot the sentence losing marks? The flaw is claiming an interpreter produces an executable file. It absolutely does not. That is strictly a compiler's job. Interpreters are used during the development and testing phase because they allow you to easily debug line by line, pausing exactly where the error occurs. Once again, we see the low-level student completely confusing basic terminology. A past paper asked to identify two different types of high-level language translation programs. Alex, our overthinker, answered PyCharm and IDLE. Alex gets 0. PyCharm and IDLE are integrated development environments. They are the overarching software suites. They are not the translation programs themselves, even though they may contain them under the hood. The top student, applying our blueprint, answered compiler and interpreter, and then correctly contrasted that a compiler translates the whole program at once, whereas an interpreter translates and executes each statement before moving to the next. Precision is absolutely everything. Look at the examiner's lens here. It heavily reinforces our golden rule. Decode the command words and stay strictly within the bounds of what is being asked. If the question specifically asks for high-level language translators, and you panic and write assembler, you lose the mark immediately. Why? Because an assembler is a low-level language translator. It seems super obvious right now while we're casually discussing it, but under the immense pressure of the ticking clock in the exam hall, students like Sam miss this tiny detail constantly. You have to read every single word of the question twice. Measure the fabric before you cut it. So let's clarify exactly what an IDE is. An integrated development environment is a comprehensive suite of software development tools used by programmers to aid the writing and development of programs. While an IDE might contain a translator, like a compiler or interpreter, it is primarily the software suite where the programmer actually writes and tests the code. It brings all the necessary development tools into one unified application to drastically speed up the process. Okay, time for Challenge 3 in our workshop, Speed Writing. Imagine a 30-second timer on the screen right now. You have 30 seconds to formulate one perfect Peel paragraph in your mind, explaining why a programmer would choose to use an IDE. Go. Think about your point. It speeds up development. Think about the evidence. What specific tools does it provide? Time's up. Let's look at the exact features you should have included in that mental paragraph to secure maximum marks. A high-scoring Peel paragraph would mention features like pretty printing. Pretty printing automatically color codes the keywords in the program and indents the layout clearly, making the code vastly easier for a human to read and maintain. You could mention a single-stepping debugger. This allows a programmer to step through the program one single line at a time, watching variables change to hunt down complex logic errors. What about error diagnostics? These alert the programmer to syntax errors and actually provide suggested corrections before the code is even run. And auto-completion provides context-sensitive prompts for long variable names, saving typing time and preventing typos. These features are indispensable. If the examiner asks you to describe an IDE, you don't just say it helps them code. You name these specific features and explain exactly how they aid the programmer. Section 5. The examiner's lens. Let's bring everything we've learned together by looking at one of the most difficult question types on the paper,
justifying the use of a low-level language.
The exam question asks why a programmer would choose to write a program in a low-level language today. Sam, our rushing student, wrote, "Nobody writes programs in a low-level language anymore as it is too hard as you have to learn special commands. 0 marks. It's colloquial, it's generalized, and it's factually incorrect." Now let's look at the green checkmark high-level answer. A program is written in a low-level language when it needs to perform a task very quickly or includes special machine-dependent instructions to operate specific hardware. Notice the beautiful phrasing there, machine-dependent instructions. That phrase is examiner gold. Low-level languages allow direct manipulation of registers and hardware. They execute at lightning speed because they don't require complex, heavy translation into machine code. Assembly language maps almost one-to-one with binary.
Answering the why instead of the how is the final thread you need to tailor the perfect exam response. As we review our final complete computer science answering system today, I want you to burn these 3 rules into your memory. These guarantee top marks. Rule 1, command word decoding. If the prompt says identify, just name the concept. If it says explain, you absolutely must provide a reason, a context, or contrast. Rule 2, Peel framework application. Point, evidence, explanation, link. Never, ever leave a raw fact hanging on the page without explaining its impact on the computer system. Rule 3, the time management matrix. Match your effort to the marks available. Don't spend 10 minutes writing a novel for a 2-mark question and don't write a single sentence for an 8-mark question. Measure the question, cut the fabric, tailor the answer.
I'll leave you with this exact past paper question to test your newfound precision. What is meant by the term debugging? Is it correcting syntax errors, finding errors by running the program, highlighting syntax errors, or stopping translation? Think deeply about the exact phrasing we've learned today. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.